By the end of this video, you will know how to attack any dynamic programming problem with a 4-step strategy. It's your lucky day. You're very thirsty, and before you is a series of bottles with your favorite drink. The problem is to choose which bottles you'll take in order to drink the most. Each bottle is marked with its volume. Drink as much as you can, but the rule is that you're not allowed to take adjacent bottles. For example, if you decide to drink from this full bottle with volume 9, you may not choose the bottle to its left with volume 5, nor the one to its right with volume 2. Our plan of attack is to ignore the optimization part, ignore the part about drinking the most, and just examine all the possible combinations of bottles. We'll examine all the solutions that follow the rule of not drinking from adjacent bottles. I'll call these valid solutions for short. In this first step, we're on the lookout for a way to break the problem into subproblems. One classic way is to consider all the elements except the last one. So let's start with the last bottle. Are we going to drink from it or not? If we take the nth bottle, then we're not allowed to take the one next to it, the n-1th bottle. The rest of the solution will have to be chosen from the first n-2 bottles. If we do not take the last bottle, then the rest of the solution can come from the first n-1 bottles. All this talk of drinking is not making me thirsty at all. So the algorithm is taking shape. We can start writing the implementation. Say we're given this list of volumes. We'll write a function that takes these volumes and returns the greatest total volume you can legally drink. In this function, which will be recursive, of course, we look at the two cases: to drink from the last bottle or not to drink from the last bottle. That is the question. When we drink from the last bottle, the solution will be the amount in the last bottle plus whatever we drink from the first n-2 bottles. When we don't drink from the last bottle, the total amount will come only from whatever we drink from the first n-1 bottles. Our second step is now to optimize over all the solutions according to the given problem statement. Here we are asked to find the most we can drink. So we'll maximize over our two cases. Let's think what happens as the size of the subproblems shrink. Eventually, we get down to the first 2 bottles. Which one should we return? The fuller one, of course. What if our list has only 1 bottle? We return that bottle. And if the list is empty, return 0. So there you have a recursive function to find out what's the most you could drink. We found the optimal solution by finding the optimal solutions for each subproblem. Let's have a look at the call tree. To keep things simple, we'll follow a small example with 5 bottles, with volumes 1 through 5. We start with the case where we do take bottle 5 and solve for the first 3 bottles. Then we split. First we do take bottle 3, and then backing up we solve for the case where we don't take bottle 3. Backing up to the root, this time we don't take bottle 5, so we solve for bottles 1 through 4. Here we split to the 2 cases. We take bottle 4, so then we solve on just bottles 1 and 2. And backing up, we don't take bottle 4, so we solve on bottles 1 to 3. Then we have the split where we take bottle 3 and when we don't take bottle 3. So now we're done. But it looks like we have repeated calculations. We solved on all 5 bottles just once, on 4 bottles also once, on the first 3 bottles twice, on the first 2 bottles 3 times, and on 1 bottle twice. So how many leaves are in this tree? Looks familiar? Where have we seen this substructure before? If you answered Fibonacci, that's right. The structure of this algorithm is the same as for finding the nth Fibonacci number, and it's just as inefficient as the non-memoized version of it. Since we have overlapping subproblems, let's go back to our implementation and memoize it. In the example we just did, we followed a general method that you can use on any dynamic programming problem. The general approach has 4 parts. In the first step, we identify the subproblems and examine all possible solutions to the given problem. This is also called brute force in a good way. This is what we did when we looked at all the possible ways to drink from the bottles without violating the no adjacent bottle rule. It's brute force, but it's smart brute force, because it leads right into the next steps. In the second step, we optimize. By optimize, I mean solve the optimization problem that we were given, usually finding the least or the most of something, or the smallest or the biggest, the lowest cost, the highest cost, the shortest, the longest. That's what we did when we took the maximum over 2 options, to drink or not to drink from the last bottle. By the end of the second step, we should have a correct, recursive algorithm that solves the given problem. However, if there are overlapping subproblems, the algorithm could be horribly inefficient. Sometimes it will run in exponential time, which makes it very impractical for real-world applications. But overlapping subproblems is actually good news, because it means that we can store the results of each subproblem right after the first time it's calculated, and then reuse those results. What's that called? All together now. Memoization. By the end of the third step, we should have a correct and efficient algorithm. It's still recursive. The call stack will get very deep as n gets large. So for practical purposes, you'll want to rewrite the algorithm iteratively. That's the fourth step. It's optional because it doesn't add correctness or an improvement in time complexity, but you often will do it as it gives another perspective on the algorithm. Now you know how to find an efficient solution to any dynamic programming problem. Starting from the top, you build a correct recursive solution. Then you optionally convert your algorithm to an iterative bottom-up implementation. L'chaim! Cheers!